Hi there, Chem12, and welcome to Unit 4, Acids and Bases. Okay, so the first three sections of this chapter, sections 4.1 to 4.3, should mostly be review. However, I would like you to read through those sections. That would be pages 109 to 115, just to make sure you review that our previous knowledge of acids and bases. Okay, we're now moving beyond that method of understanding acids and bases, and we're now going to talk about this Bronsted-Lowry. Okay, so the Bronsted-Lowry theory is a little bit different in terms of what we're looking at for what an acids and bases are. So in Bronsted-Lowry, an acid is a proton donor, okay, and a base is that proton acceptor. Okay. Now the acid part is probably very similar to what we dealt with in the past, because when we're talking about a proton, we are talking about that H+. Okay, whereas a base being that proton acceptor, it's a little bit different than what we normally think of it, because normally we would think of providing that OH- into the system. Okay, so just want to be careful with that. We are now talking about a proton donor and a proton acceptor as our acid and base. All right, so I've asked you to consider that equation there where we've got ammonia plus water, okay, and from here we are forming then that ammonium, NH4+, and that hydroxide, that OH-. Okay, and so what we're looking at here is, in this situation, it's actually the water that's donating our proton. So although we never really think of it that way, that makes water our acid in this situation. And it's the NH3 that's gaining that extra proton, which makes it the base. Okay, actually I'm going to switch colors there. And I'm going to go red for base. Okay. And while we have those, like I said, this is the accepting the proton, that's donating the proton. We mentioned a little bit later on here where we're talking about these conjugates. Okay, so if this is our acid, that makes this OH- our conjugate base. Okay, because these two substances are only different by one proton, and that makes them a conjugate acid-base pair. If this is our acid, the OH- is our conjugate base because they only differ by that one proton. Similarly, we have our NH3 being our base, and that makes this NH4+ our conjugate acid. Okay, because these two substances differ by that one proton again. So the NH3 and the NH4+ are a conjugate acid-base pair. Okay. Now, after we talk about these, the new definitions of our Bronsted-Lowrys, okay, we start talking about these different acids, because we're talking about this proton donor. Well, things don't necessarily have to supply just one proton. We can provide more than one proton, okay? And so what we're talking about here is we have this monoprotic acid, okay? And that can donate one proton. A diprotic acid can go up to 2 protons. Okay? It doesn't have to donate both. It can donate just one, but it has the ability to donate up to 2. We have the triprotic is up to 3 protons. Okay? And in general, we use that term, the polyprotic acid for any of these acids that can supply more than one proton. Okay? So product, just talking about those protons that we can donate. The mono, di, tri being the 1, 2, 3, and then poly, just a general term for more. All right. Now, we also have another term here. We're talking about this amphiprotic. Amphiprotic. Okay? This is something that can accept or donate a proton. Okay, so I've got a couple examples there. We've got H2O, we can say H2PO4 minus, or the HS minus, just as a few different examples. Okay, especially if we're looking at here, we've got this H2PO4. I've still got another proton I can donate, but I've also got a negative charge, which means I can accept that proton, right? So from here, if I donated another proton, I would be HPO4 2 minus, whereas if I gained a proton here, I would be H3PO4. Okay, so we do have a couple options on this one. Let's take a look though at water. Okay, water tends to be the most common amphiprotic system that we're dealing with, but also any of those di or triprotic acids, once they've donated a proton, they become amphiprotic. Now, if we're looking at water, okay, well, if we start off with water and we add a proton, well, this gives us that H3O plus, okay, the hydronium ion. Or if we take that H2O, it can also, so here's accepting the proton, we can also donate that proton and also have then that hydroxide ion. Okay, so this is showing that amphiprotic nature of water. We can gain a proton, making it act as a base to become the H3O plus ion, or it can be the H2O where it donates that proton and we have that OH minus. Okay, so be careful here. Amphiprotic if it possesses a negative charge and has an easily removable H plus or a proton, then it is amphiprotic. And then we've also got this situation where we're talking about water. Okay. Now, that was our example with water. Let's take a look at another one here, where we are going to talk about, let's talk about this HCO3 minus. Okay. Now, if I combine this situation here with, say, Cn minus, we form an equilibrium situation with a CO3 2 minus and HCN. Okay, and in this situation, this HCO3 is acting as an acid. It's donating a proton to here. Okay, now we've got the other situation also where we've got this HCO3 minus, and let's say we threw that into some just water. Okay, from here we form a equilibrium reaction with H2CO3 and OH minus. And in this situation, it's accepting a proton from the water, making this a base. So these amphiprotic substances can act as acids or bases, as we've shown with the water and with the HCO3 minus. Okay, so we were talking about this conjugate acid-base pair, right? So in this top one, we've got HCO3 minus is acting as an acid. Its conjugate base would be the CO3 minus. So I'll put that as the CB. Okay, so we've got our acid and our conjugate base. Whereas when we had it acting as a base over here, then this over here is our conjugate acid. Right? They differ by one proton, our base to our acid. And same up here, our acid to our base, we differ by one proton. Okay? Alternatively, that would make our Cn minus in here our base, and that makes the HCN our conjugate acid. Or if this was our base, that makes the water our acid and makes the OH minus our conjugate base. Okay, so that is a majority of the definitions we wanted to take care of, but we've also got a little bit other information to talk about. All right, in your notes, you'll notice that I've got a comment here about being aware of some organic molecules. Okay, so a couple organic molecules can act as acids or as bases, depending on what we're looking at on these. Okay, so when we're looking at the citric acid, I mean, it does tell us it's an acid in the name, but what we're really looking for is these COOH groups. Okay, we see this in acetic acid. Okay, but we also see it happening here in the citric acid. In fact, we've got 3 of these COOH situations. We have 1, 2, and 3. Any of those could then be a proton donor donating these protons on the OH. Okay, so that's where these organic molecules can become acids, or if we're talking about an organic molecule acting as a base, what we're looking for is this amine group, this NH2 or an NH, can act as the proton acceptor, turning this into an NH3, or if it was an NH, becoming an NH2. Okay, so we just want to be careful of those. So a couple organic molecule drawings for you. Okay, folks, I realize I don't have this for you on your on the worksheet I've given you, but I'd like you to try this example. So what I've got listed here is a couple molecules that are going to act as acids and a couple molecules that are going to act as bases. What I want you to do is, if I've given you the acid, write out the base. If I've given you the base, write out its conjugate acid. So pause the video and take a look at figuring those ones out. All right, well, hopefully you've gone through those, and let's go through these solutions. So if this is our acid, that means it's donating a proton, so I need to remove an H plus to make its conjugate base, which would leave me then with HC04 minus. If this is my conjugate base, then to make its conjugate acid, I need to add that proton. So that gives me HSO3 minus. Okay, remember, a conjugate acid-base pair is only differing by 1 proton. Okay, so we're not going to try to completely eliminate this negative charge. We're just going to add that 1 proton, and we now have that conjugate acid-base pair. Okay. Down here with our HCO3 minus, now this is an amphiprotic situation, so we got to be careful. We're going from the acid to its conjugate base. Again, we need to remove that proton, leaving us with a CO3 2 minus. Okay, and again, last one here, we're dealing with H2O. If we want to come up with its conjugate acid, we need to again add that proton, giving us H3O plus. Hopefully you're able to get all those right. Okay, next up we want to talk about the comparisons here between strong and weak acids and bases. So we got to be careful here. Strong acids and bases are 100% ionized in solution. Anything less than 100% is considered weak. Okay, so we usually talk about the strong and concentrated and weak and dilute together, but there is very big differences between those. Okay, so remember that strong acid or base is 100% ionization. Okay, so and then a weak is just considered anything less than 100% ionization. Okay, so we're talking about its ability to disassociate from its protons. Okay, so completely donating protons or completely accepting protons, whereas a weak is we're going to have an equilibrium situation. Okay, So I can give you an example here. A strong acid, we are going to take, say, hydrochloric acid plus water, and we are going to go to completion to make Cl minus and H3O plus. Okay, going to completion. Whereas a weak acid, we can consider, say, acetic acid, one of those organic acids, okay, CH3COOH, plus water. Now this one is going to be in equilibrium with that CH3COO minus and H3O plus. Okay, strong acids go to completion, strong bases go to completion. Weak acids or weak bases form an equilibrium situation where we still have some of the acetic acid in combination with some of the acetate ions in solution. So we've got to be careful with those definitions. Okay. Also, if we're looking at concentrated versus dilute, okay, for these concentrated versus dilute situations, we're looking at a high molarity, okay, a high number of moles per liter, versus dilute would be a lower molarity. Okay. So usually for a concentrated one, we could be talking about, say, 18 molar sulfuric acid or a 12 molar hydrochloric acid. Whereas if we're talking dilute, even a 1 molar, sorry, that doesn't look like an M, a 1 molar sulfuric acid, okay, it's much more dilute than a concentrated one here. Or we can talk about, say, a 0.5 molar or 0.1 molar HCl, okay? So we can have a dilute strong acid, right? If we had a 0.5 molar hydrochloric acid, that's going to be a dilute strong acid. It's going to go to completion, but it's still going to be fairly dilute. Or I can even talk about a concentrated, instead of maybe this 12 molar hydrochloric, let's talk about 12 molar acetic acid. We're dealing with a weak acid, but it's still very concentrated. Okay, so you just want to be careful with those two situations. All right. Next up, I'd like you to just kind of take a look at the very back of the textbook. In our data tables here, we have an ionization chart. So we've got the relative strengths and weaknesses of Bronsted-Lowry acids and bases. Let me find my textbook here, and I'll open up that data table, and we're just going to take a look at that one together. So that's going to be, I believe, on page 334. Have it right here. Okay. So as we're looking at this sheet here, okay, we want to pay attention that all of our strong acids are sitting up here at the top. We only have 6 of them, okay? And one thing I want to point out is when we're talking sulfuric acid, we're only talking about the H2SO4, okay? If we're talking about the HSO4 minus, we're going to see that sulfurous, or the hydrogen sulfate ion down here, this is actually in a weak acid situation. It's only the first proton in our sulfuric that's actually a strong acid. Once it turns down into the HSO4, it's now a weak acid. Okay. Also, if we go down to the very bottom, we'll notice we've got a couple of our strong bases. Okay, so NH2 minus or O2 minus, both of those are going to strongly attract a proton and go to the NH3 or the OH minus. Okay. Another one that would also be considered in here would be the OH minus of those metal hydroxides. Okay. Now remember though, these are low solubility salts, so they have a little bit of a different impact, and we'll talk about that later on. Okay. So just when we're looking at this, the stronger the acids are up to the top, the stronger the bases are at the bottom. Okay, we've only got a few completely strong acids. Everything else is in the weak section. Okay, but we have a differing degree of those. And we'll come back to these a little bit more as we talk about the Ka values in future lessons. Okay. Now, I just want to take a look and see if we have an understanding here. I want to know, what do you think is the concentration of ions in 1 molar nitric acid? Okay, so we want to find nitric acid on our sheet there, and we realize that it is at the top in our strong acid portion. So we could say then that the concentration of H plus is equal to the concentration of NO3 minus, which equals 1 molar. We've got a 1-to-1 ratio and we have full ionization. However, if we are looking at the concentration of ions in a 1 molar CH3COOH, okay, both of these ions that we're going to talk about here, we've got the CH3COO minus and that H plus, okay. Both of these are going to be less than 1 molar. We haven't gotten to the point where we can calculate these yet, but we notice that this is in the weak acid, meaning it's not 100% ionization, so we're going to end up with less than 1 molar of the acetate and the H plus ions in there. All right, so hopefully we have a little bit of understanding of our new definitions of acids and bases, being aware of the Bronsted-Lowry definitions that we're using, understanding the strong versus the weak, the concentrated versus the dilutes, and hopefully start to take a look at that data table at the back of the textbook. Okay. So as I said before, please read the sections 4.1 to 4.3. Okay. In 4.4, we've got questions 13 and 14. 4.5, questions 16 to 19, and then in 4.6, 21 to 27. That should take us through the end of this week. I'll see you next week. Be safe, stay healthy.